Hi everyone, I hope you're all doing well. So in today's video, I'm actually going to go through the 2017 chemistry exam multiple choice section. Like always guys, before I start this video, if you guys want private tutoring in specialist methods, physics or chemistry, you can always email me through this email. Guys, we also have, just launched our website. If you guys want to check it out, it'll be in the link in the description. We have tutoring packages, we have also some practice exams down there, and we also have some notes for some. Hopefully, currently we do have some physics notes, but hopefully we can make some chemistry and specialist and methods notes in the future. So yeah, if you guys want to check them out, they'll be in the link in the description. So yeah, let's start this exam. So question 1, a catalyst. Okay, so what is a catalyst? Let's first understand what a catalyst is. A catalyst is a substance that decreases the activation energy of a substance. So what it does, let's have a draw of this. We know it decreases the reaction rate. It decreases the activation energy. So for example, a reaction, let's say a reaction goes like this. And it goes like this, but goes up and goes down. Okay. So what is the activation energy? Well, the activation energy is from here to here. Pretty much this is your activation energy. So what a catalyst does is it decreases that activation energy. So remember that activation is the minimum energy for the reactant to go to the product. So if we decrease that, what do we get? We get more success. So the reaction becomes more successful if we decrease the activation energy, but also we get a faster reaction rate. So that is what a catalyst does. It increases the rate of reaction, and it doesn't even get used up too. So let's have a look at the possible answers. A catalyst slows the rate of reaction? No, it increases the rate of reaction. The reaction actually goes quicker because the activation energy has decreased. So A is wrong. Ensures that a reaction is exothermic? No. A catalyst does not show you that it's exothermic. A catalyst works for both endothermic and exothermic. So 4B is wrong. So is it moves the chemical equilibrium of a reaction in the forward direction? Okay, guys, a catalyst does not affect chemical equilibrium. This is very important. A lot of students get mixed up with that. Remember, a catalyst does not ever do anything with equilibrium. Whenever you hear a catalyst with equilibrium, it does not affect it. So absolutely, C should be wrong. D, provides an alternative pathway for a reaction with a lower activation energy. Yes, it decreases the activation energy, so a new pathway is created. So D would be your possible answer for that one. Question 2, lithium-ion rechargeable batteries are used in mobile phones. Environmental conditions can affect the number of charge cycles for a lithium-ion battery until its end of its useful life. Which of the following environmental conditions would be expected to result in the largest number of charge cycles for a lithium-ion battery? So we want the best conditions for a battery to have the highest life cycle. So we want the battery to have a very long life. So what are the best environmental temperatures? Okay, you should know that. Okay, when a battery has a very high temperature, what happens is the charge cycle actually decreases, because when you're increasing temperature, you're increasing the rate of reaction. And when you're increasing that rate of reaction, the side reactions also increasing, meaning that those side reactions is the reactions that we don't even want. So if those side reactions are happening, they actually destroy the battery life. So hence high temperature, very, very high temperature will decrease the life cycle, its useful life. Also, having very much low temperature is also bad. So because what it does is actually decreases the charge. It decreases the discharge. So, and that kind of really much affects it. So, but in any case, I think you should know that having very much high temperature is worse than having low temperature. So just remember, having both of them, having very high temperature is very bad. Also, having low temperature is very bad. But having a low temperature is a little bit, in the middle. It's very efficient for a battery then compared to very high. So let's look at this. I'll actually just show you a graph of how this looks like. So just to explain it much more nicer. What it looks like this. So you have your life. percentage, say, life percentage of a battery, and this is your temperature. Say the temperature is like maybe 8. So 8 degrees is very nice. So it's like kind of cold. It's a little bit also a nice, and let's say the highest temperature we'll go to is like 100 degrees. And the lowest temperature will go is like negative 50 degrees. Something that's very high. Yeah. So this is your temperature in degrees Celsius. And this is how the actual thing should look. So it's optimal. It's the most maximum life would occur in the middle, where it's both between the hot and the cold. But the life decreases for when you go greater than that. As you go greater and greater with high temperature, the life becomes less. As you go, decrease from the as you decrease the temperature very low, also the life decreases. So that is very important to know. So it has to be a very good temperature. Let's look at our answers. So minimum temperature negative 8 to 11. This is very, very low. No, negative 8 degrees Celsius is very, very low. It's very cold. B, 9 to 21. Yeah, you can say that's good. So the maximum temperature is 21. So remember, the room temperature is around 25. So yeah, it does sound, it's very good actually. So put a question mark on that. We'll leave it there. C, 18 to 37. Look, 37 degrees Celsius is very hot, by the way. Especially if you live in Australia, it's very, very hot. So yeah, that's a problem. If maximum temperature is that and 18 is, so yeah, C is also possibly wrong. D, okay, maximum temperature is 40. No, this is also very, very hot. And you should know that for C, it should be also wrong, because remember that if you have an iPhone right now, currently, like for example, my iPad, when it's charging and it gets very hot, especially in a hot day, especially in the summer, what happens is the actual, it doesn't charge anymore. It's because it tells me, like the Apple, it tells me that we can't charge because it's a very high temperature. So it's important that even 37 degrees is very high, especially living in Australia. So yeah, make sure that's not good. So B would be the best possible answer. It's a nice, it's also a little bit in that low temperature, which is great. It's kind of in that nice temperature. So yeah, hope that makes sense. Question 3, a hydrolytic reaction occurs when? Okay, hydrolytic. Hydro meaning water. So I think hydrolytic just means hydrolysis. So if you write hydrolytic and hydrolysis, yeah, they mean the same thing. As you see, hydro means water, lysis means breakdown. Hydroly, and then have tick. So I think it's just a quick way of saying a hydrolytic reaction is just a hydrolysis. So what we want to see, which one of these gives us a hydrolysis reaction? Let's have a look. So a hydrolytic reaction occurs. Remember, what is a hydrolytic? It is the breakdown. So when we break down something, we pretty much put in water. So the reactant is water, because we are putting water to break down. For example, we break down fats, we break down proteins, and we break down carbs using hydrolysis. So that's very important. So a dipeptide is formed? No. When a dipeptide is formed, that is a condensation reaction. And guess what? The water is actually on the product side. It's not on the reactants. We're not using water to break down. So yeah, a triglyceride is formed. Also wrong. Remember, fats, proteins, carbs, always when they are being formed, it's a condensation reaction. It's not hydrolysis. Water is a reaction product. Okay, wrong. Remember, water has to be in a reactant for a hydrolytic reactions. The glucose is formed from maltose. Yes, glucose. So imagine having maltose is an actual 2 sugar. It's a disaccharide, and when you're putting into water, for example, when you're using a reactant of water, it breaks that down through hydrolysis, and then we get two glucose molecules. So D is right. Question 4. Which of the following contains a chiral carbon? So to know what carbon is chiral is, this is how the form is. It has to have 4 single bonds. And each side of these has to have a different actual atom. For example, if I have chlorine here, I have hydrogen, I have bromine, and I have iodine. Can you see how all of these over here are different molecules that are around the carbon? This, hence, is chiral because all of the atoms are different. But what about if, for example, let's say this was hydrogen. Now, this over here is not chiral because there's two of one thing into it. There's two hydrogens. They're supposed to be, each of the sides are supposed to have its own specific, so different atom. So, and it also needs to have single bonds, always. Chiral has to have single bonds. So let's look at the first one. So it says 2-methylbutane, 1-ene, which is this. Let's draw that. So it has a C and it has a C2, so it probably has a double bond. So we have H's here. And it's a C, and we have a CH3 here. C. Okay, we have this. And what can we see for the first one? Let's look at chiral. Well, see, this is not chiral because can you see there's two hydrogens. There's actually three hydrogens, to be honest. This one also two hydrogens in the same carbon. Nope. This one, a double bond. Both of them have double bonds, so absolutely wrong. So 2 is wrong. Let's try the next one, which is so it's this CH Cl C this. Okay, so it looks like this. Okay, so what can we see? Let's look at if there's any chiral carbon. So this one's absolutely not. This one over here also not because it has two hydrogens. This one has a hydrogen. That's different. So Cl, that's good. That's totally different. On the side, it has a methyl group. That's great. And then it has a ethyl group. So all of them are different. So this carbon overall has its chiral. So B is supposed to be your answer for that one. Great. Question 5. Which of the following is a biofuel? Remember, what is a biofuel? Well, a biofuel is the definition of a biofuel. This is what I always tell students. So just think of it. So biofuel. So when you're talking about consumption, consumed, replenished. I always say replenished. So we have oh my god, did I even replenished? Did I just think? Okay, so we have replenished and consumed. So we know that for a biofuel, we know that it has to be greatly higher replenished than it is consumed. This is very important. This is for a biofuel. This is the definition of biofuel. So it's pretty much a biofuel is a fuel that is greatly replenished or greater or equal. So it's replenished greater or equal to then it's consumed. So yeah, so we know its replenishment is greater when it's consumed. That's what a biofuel is. So let's look at the questions. Ethanol is produced from crude oil. Okay, no, crude oil is a fossil fuel. Absolutely not. Ethanol produced from cellulose. Okay. Cellulose comes from plants, and plants, we can grow them very quick. Like they can be easily replenished, greater than they are consumed. So B is probably right. Yeah, B looks great. Cellulose. Propane produced from natural gas. Natural gas also a fossil fuel. Be careful with that one. Electricity produced from hydropower. Hydropower, no, absolutely not. Hydropower is also pretty much a fossil fuel. And yeah, that's pretty much it. I hope, yeah. Question 6. The overall equation for a particular methanol fuel cell is shown. We have this, so we have a fuel reacting with oxygen, and it gives us that. The equation for the reaction that occurs at the cathode in a fuel cell is what? Let me just tell you a hint. Whenever you're dealing with a fuel cell, if oxygen gas is reacting, it will always occur at the cathode. Always. And the fuel itself always acts at the anode. That is, if oxygen is, reacting. Well, in this case, oxygen is reacting with a fuel, meaning that if we want the cathode in this reaction, cathode is the reduction. So we know for a fact that from our O2, our oxygen, it's always get a cathode. It's going to be the cathode. So we know this one over here, it's going to go through reduction. So if your oxygen gas is going through reduction, we know that the electrons might be on the left. It has to be on the left. So let's look. This one's good because it does, let's see, so it has oxygens on the left, but the problem is it's carbon dioxide that's reacting. Remember, O2 is the cathode, so O2 is being reduced. That's wrong. B, again, this is a fuel, and also it's being oxidized. Remember, it's been O2 must be reduced to be in the cathode, so don't. C, okay, we see it's O2, so O2, that's great. And it's also being reduced, so that's great. So possibly C would be your answer in that one. D, okay, this one, they're on the right, so the electrons are on the right, meaning that it's oxidizing. No. So it has to be a cathode where it's being reduced. So D is also wrong. So C is your possible answer for that one. Question 7. What is the total energy released in kilojoules when 100 grams of butane and 200 grams of octane undergo combustion in the following presence of excess oxygen? Nice and easy. So, okay, let's look at our energy, for example. Sorry. Let's look at our energies for butane here. So right over here. So we're looking at butane. So if I where is butane? So we're looking at butane and octane. So what are the energies? Because we are dealing with grams, we're going to use this one over here. So for butane, it's going to be this one. And for octane, it's going to be this one. So let's write that down. So for butane, let's calculate the energy for butane. We know butane has 49.7, and it's in terms of kilojoules per gram. So I'm going to write equals to kilojoules per grams. And what about octane? So octane has 47.9, and also it's in kilojoules per grams. I like to write them like that, so the units in terms of that, because I can easily calculate using the units. For example, if I know I have 100 grams of butane, so 100 grams, it's in terms of grams, so what I can do is I can sub in the 100 here, because this is our grams. I sub it in here, multiply them together to get in terms of kilojoules. So in other words, what we're saying is what is the energy. So for energy of butane, I'm going to write B. Energy of butane is going just to be 49.7 times the 100 grams, which gives us 4970. It's because it's kilojoules, we have to write kilojoules. And what about the energy of octane? So O. Again, it's the grams, which we have 200 times 47.9. So 47.9 times 200, and we get 580 kilojoules. And adding them all together to get the total energy, we get 4970. So add that. We get 14,550 joules, which looks like B is your possible answer for that one. Nice and easy. Question 8. An enzyme. Let's actually make this little, because we've taken the space quite a lot. So let's put that here. Okay. It says, an enzyme can distinguish between optical isomers. Let's check that. Wait. So if we have an enzyme, this is the best. Let's say we have an enzyme. And remember, enzyme has a specific active site. So for example, let's just draw. Let's say this here is your enzyme. So this part is your enzyme, and it has a specific active site. So let's just draw like a square in the middle, a triangle, a circle, and say we have an isomer. So like so what an optical isomer, it has its own mirror image, and they cannot be superimposed. For example, let's just draw a chiral compound. So for example, let's say this. So we have this. Let's say it's like a star here. Okay, now this pretty much isomer, so this original isomer, it can actually fit into the enzyme. So it will react with the enzyme. That's great, because when you put it down, these nicely fit into the perfect spots here. It's optical isomer. So if I draw a mirror image and draw this, so the same diagram. So again, because remember that this is the enzyme, and the enzyme is going to be the same. Let's put the enzyme here. And now we're taking the mirror image of this, which is going to be, again, the star's still here. And now the circle is going to be here. The square is still going to be there. And now the triangle. Now this actually doesn't fit inside the thing. Can you see the circle and the triangle? So what it actually can. An enzyme, because the enzyme, for example, let's call this, I don't know, let's say it was vitamin C in this case. I don't know, vitamin C. And This is its optical isomer. And we're like, can an enzyme, for example, this enzyme, distinguish between them? Yes, it can, because say we have the real vitamin C that actually does work with the, does actually react with our enzyme, but let's say we had the optical isomer, and the way we can distinguish is, what about if we put the optical isomer with the enzyme and it doesn't react? That tells us it's the optical isomer, so it can distinguish. So A is actually possibly right. We can put a tick in that one. That's actually, yeah. So that's nice and good. So let's look at the next. Let's put a tick. B, catalyzes the forward and reverse reaction. That's true, yeah. An enzyme can. Remember, if you just draw an energy profile diagram, for example, if you draw a nice energy profile diagram, what can we see? It's, so for example, so we draw like this and it goes like this. Now an enzyme, what it's going to do is it's going to decrease. It catalyzes, so it decreases this activation energy, and so when it catalyzes, it like catalyzes the forward. Pretty much, it catalyzes the forward, which is going forwards, but it also catalyzes. It can also catalyze the backwards reaction if we go this way. So also, A and B are possibly right in that one. They don't look bad. C always needs a coenzyme to function. No. Some need a coenzyme, not all. Is not able to change shape. That's rubbish. There is two models. There is the key model, key unlock model, and there is the induced method. The induced, the active site actually changes shape, so the enzyme changes shape. So that's wrong. So we have A and B. I think overall, both of them are right. Like in terms of understanding, like both work. Like an optical isomer can actually be distinguished using an enzyme in that case. But which one would be the most correct? Have I made a mistake here? Because both of them are actually correct here. I'll put A as right, because we did show that. Whereas catalyzed forward reaction, yeah, also that's also correct. So I'm actually going to put both of them. I got to check the answer after. Actually, yeah, I'll have to check the answer for this one. But I think both of them are right, because they both meet the requirement. Let's move on. Question 9. The nutritional information panel on a packet of muesli includes the following information. Okay, so the average serving size is 45 grams. Average quantity per 100 gram is this. So we have protein, fat, carbs. Okay, using the information above, the percentage energy content due to protein in an average serving size of this muesli is what? Okay, that's not too bad. So we want the energy of the protein, so protein, all divided by the energy of the total, which is the protein, plus the energy of the carbs, remember carbs, plus the energy of the fats. We only take those as our total energy, and then we're going to multiply it by 100 to get the percentage. That's what we're going to do. So it says in the average serving size. It really doesn't matter. You can take 45. I mean, they'll still give the, in terms of percentage, you'll still give the same answer. So I'm just going to use that 100 grams. So we'll do that. So if we go to our formula sheet and say what are the energies of proteins, let's write those down. So I want to write it here, energy of pretty much, oops, so energies for protein, it's over here. So for the protein, we know proteins have a 17 kilojoules per gram. Also for carbs, it's 16 kilojoules per gram, and for fats, it's 37 kilojoules per gram. That's it. So we have those energies. So to get that energy in terms of remember writing the formula like for the protein, it's just 17 kilojoules per gram is just equals to kilojoules per gram. So if we have the mass, in this case, we do have the mass of the protein, multiply that with that, and we get the energy in terms of kilojoules. So that's important. That's great. So what's 17? So for the energy of the protein, it's going to be 17 times the 13.2, which is what? So 17 times 13.2, that gives me 224.4 kilojoules. Okay. Energy of the carbs is going to be 16 times how much carbs do we have? We have in total 48 48.2. So 16 times 48.2, which gives us 771.2. And what about the energy of fats? I remember all of these are in terms of kilojoules, so yeah, energy of fats is 37 times. How much fat do we have? Well, we have in total 16.3. 16.3, and that gives us 603.1. And remember, using this formula, protein's 224.4 divided by the total. So the total is going to be 771.2 plus 224.4. The total is 1598.7, and we multiply that by 100. So 224.4 times it by 100, and we get 14%. So C is your answer for that one. Nice. Question 10. Which of the following structures represent a sweeter ion of a 2 amino acid? Okay, 2 amino acid is just an alpha amino acid. So when you're doing in chemistry, you're going to be dealing with always 2 amino acids. Like 2 alpha amino acids. So which one represents a sweeter ion? What is a sweeter ion? A sweeter ion is a amino acid that is neutral. The charge cancels out to 0. And yeah, pretty much that's what a sweeter ion is. So having a look at the first one, let's look at it. What is the overall charge? It is negative. Can you see how it's a negative here? It tells us that this whole charge is negative. So it's actually not neutral. So A is wrong. It needs to be neutral. What about this one over here? This one is just positive. Can you see that positive? This one over here, C, we can see positive, negative, cancel that. But we also have another negative. So there's more negative than positive. So hence, the overall structure is negative. It's not a neutral. D, this one's nice. Positive, negative, they cancel out, and that's it. Choose D as your answer. Question 11. A galvanic cell consists of 2 connected half cells that can produce an electron flow. Which combinations of standard half cell pairs would be expected to result in a cell potential of 1.41 volts? Nice and easy. So to do that, what I'm going to do is go to my electrochemical series. A very common question. This is a quite very common and easy question to do. So if you look at that, okay, let's look at the first case. So we have a aluminium electrode and a Ag electrode, and let's look at it in our electrochemical series. So we're Al. Where is Al? First, Al is over here. So Al is going to be this one over here, and it's reacting with Ag. Where is Ag? Let's go from the top to bottom. Ag is over here, which is over here. We always, to get the actual overall cell potential, what we do is we, the top minus the bottom, always. So in this case, what we're saying is, what is 0.8 minus 1.66? That gives me 2.46. So this pair will give me will give me 2.46 volts, and that's not what we want. We want 1.41. Let's try the next case. So I'm just going to rub these over here, and let's try the next pair. The next pair is zinc and nickel. So zinc and nickel. Let's try that. So where is zinc? So I have nickel over here. So nickel's over here. What about zinc? Zinc is over here. Let's do that. So we're going to say the top, so minus 0.25 minus negative 0.76. And that gives me 0.51. Not what we want. So 0.51 volts. Let's try the next pair. So the next pair is nickel and aluminium. Let's do that. So we have aluminium over here, and we have nickel over here. So minus 0.25 minus negative 1.66, and that gives me 1.14. So yes, 1.41 volts. So your final answer should be C for that one. Nice and easy. That is your overall cell potential. Great. Next question. Question 12. When stored under identical conditions, which of the following fatty acids is likely to undergo oxidative rancidity in the shortest time. So which one will go the quickest for oxidative rancidity? Now, okay, what is oxidative rancidity? It's pretty much when you take fats and when they react with oxygen, they smell bad. They start to smell bad. And so what it is we take a fat, for example, a fatty acid. So, and fatty acid, and what it does, it reacts with oxygen gas. And what does that do? It results in a ketone. Normally, it results in like a ketone and an aldehyde. And what, if you don't know, ketone and aldehyde, they smell like rubbish. Yeah, some of them smell very bad. So, and why does oxygen when reacting with that happen? It's because I'll tell you how. So when fatty acids, it only works. So oxidative rancidity only works on fatty acids that are unsaturated, meaning that those that have double bonds are the ones that actually go through oxidative rancidity. It's because when you have, let's say, an oxygen, that thing wants to break down that double bond, and that results in a ketone and an aldehyde, likely. So pretty much the more double bonds a fatty acid has, the more likely that this oxygen will want to react with it and break that double bond and create a ketone and an aldehyde. So that's what we don't want. So if for this question, it's saying which one will undergo oxidative rancidity in the shortest time, which one will go with the fastest. So pretty much what we're saying is which one has the most double bonds. So the more double bonds, the more oxidative rancidity. Let's check that. Very easy by just using our data booklet. Have a look at this. So go down and we're going here. Yes. So the first one is linoleic acid, which is over here. And have a look at this. If you look at it, how many double bonds? Have a look at here. There is 3 of those double bonds. So this one actually has 3 double bonds. Okay. The next one is linoleic acid, which is this one over here, and it has 2 double bonds. And what about stearic acid? So I hope I'm saying those right. Stearic acid has no double bonds. So okay, this one's not going to go for oxidative rancidity. And what about oleic acid? Oleic acid, which is this one, has only, where is it? Has only 1. So it only has 1. So like we said, the one that will go for oxidative rancidity has the more double bonds. So it'll be A as your answer. Linoleic acid has more double bonds. That's it. This question. So 4 identical vehicles, model 1, 2, 3, 4, were tested for fuel efficiency using LPG, petrol, unleaded 91 octane, E10 petrol, 10% ethanol added, and petrodiesel. Carbon dioxide, O2 emissions per litre of fuel burn were also determined. And the following table summarizes the results. Okay, the first question. Question 13. Using the information in the table above, which of the following statements about petrodiesel is correct? It has the highest energy content. Let's check that actually. So to think about energy content, let's look at in terms of fuel consumption. So this is how much every of each fuel will take, in terms of liters. For 100 kilometers, let's say for car 1 to go for 100 kilometers, it will take it needs 19.7 liters of fuel. So the ones that is the lowest, the one that which is in this case petrodiesel. So petrodiesel takes the lowest liters. Means a car. So car 4, when it travels 100 kilometers, it only takes 9.2 liters. So it's very efficient. So the petrodiesel is very efficient actually, and also it actually has the highest energy content. Remember, because if it's going through 100 kilometers, all of them are going through 100 kilometers. But this one over here is this one it needs 19.7 of liters, whereas 9.2. So petrodiesel has so much energy. It has actually an overall high energy content that it only needs a little amount of liters, a little amount of volume to go that 100 kilometers. So I hope that makes sense. So that is true. It has the porous fuel efficiency. That's rubbish. It has the highest, as we see. For 100 kilometers, it only needs 9.2 liters. So it's actually the most efficient one. So that's wrong. C, it is a renewable energy source. That's absolutely not. It's a, it's petrodiesel is a fossil fuel. It has the lowest CO2 emissions when burnt. So, okay, well, let's look at the CO2 produced. It actually produces the most from all of them. So that's wrong. It actually produces the most CO2 emissions when burnt. So the possible answer for that one is A. Nice and easy. Next question. Question 14. So the use of which vehicle has the smallest impact on the environment in terms of the grams per CO2 produced per 100 kilometer? Nice and easy, actually, because here, let's look at this. Let's have a look at this. This is what we want. This is grams of CO2 that will be produced for each fuel per liter. If we know that for the 100 kilometers, let's actually calculate. So for the LPG, for every 100 kilometers, it takes 19.7 liters. So we know for 100 kilometers, it takes 19.7 liters. And we know that this is the amount of grams of CO2 produced every liter. So for this car, because it's traveling 19.7 liters for the 100 kilometers, we just multiply this with this to get the grams of CO2 produced. So let's do that. So 19.7 times 1665, and that gives me approximately 3,800 grams. We'll do the same, so multiply this with that. They're pretty much all the same, and we'll find out which one has the least CO2 emission. So 14.5 times 2392. So one's 34684 grams. The next one's 2304 times 14.2. This one's, so this one actually is supposed to go like this, yeah. The next one is 32716. Next one is 9.2 times 2640, which is 242888. So, which one actually produces the most less CO2 in terms of gram? Petrodiesel. So vehicle 4. So choose D as your answer. Yeah, nice and easy. 3 calculations, and yeah, hope that's right. Question 15. Which of the following is the correct statement about the denaturation of a protein? The denaturation. So the denaturation is the disruption of the secondary, tertiary, and the quaternary structure of a protein. That's what it is. So for this question, denaturation, for question A, denaturation is characterized by the release of peptides. No. The release of peptide, remember, that is the primary structure. The primary structure has, peptides. So, like, for example, these all amino acids, and these are all peptides. So the release of them is pretty much what we're saying is, the denaturation is the release. They're pretty much saying the disruption of the primary structure, which it's not denaturation. Denaturation only happens for secondary, tertiary, and quaternary. Next question. Alcohol denatures proteins by disrupting their hydrogen bonding. Well, let's check that actually. So, for example, let's say we had a molecule, and let's say we had another, and so we have some bonding. So, example, say we had like a OH bond here, and we say we had an actual OH bond here. So what can we see? There's going to be, of course, hydrogen bonding that occurs between them, and that's what actually is the structure. So let's call this a tertiary structure, and so there is actually some hydrogen bonding occurring. And let's say we put a alcohol, for example, methanol, CH3OH. So we put methanol into it. So we'll write it as CH3OH. What's going to happen is it's actually going to, because it's going to, again, form, hydrogen bonding. So it's going to form hydrogen bondings. That's true with the sides. But the problem is it also has, so it kind of does disrupt it because it does create some hydrogen bondings with the supposable, the actual hydrogen bond. So it does create some hydrogen bonds. So it can weaken the other hydrogen bondings. But also because there is the CH3, this non-polar group here. This non-polar group, what it can do is it can kind of disrupt the actual remember the hydrogen bonding. So remember, this is going, so this is very polar, and then you get, a non-polar side. For example, it's not methanol, it could be like propanol, like a very high non-polar group, and it actually pretty much does disrupt it. In a case, it can disrupt it pretty much. So alcohol denatures protein by disrupting the hydrogen bond. So denaturing is the breaking down of the side reaction. So it can actually do some damage. Yeah, alcohol, because it does form hydrogen bond. I hope that makes sense in a way I'm explaining it. Yeah. So let's look at the next question. So C, let's look at C. Denaturation involves denaturation involves disruption of all bonds in the tertiary structure. Absolutely wrong. Tertiary structure, what are the bonds? Well, we have, hydrogen bonding. So we have hydrogen bonding. We have disulfide bonds. We have ionic bonding. We have quite a lot of ionic bonding. We have quite a lot. These are just the major ones. But so denaturation, it does pretty much destroy the hydrogen bonding. But in terms of disulfide bond, it doesn't actually affect the disulfide bonds. Remember, disulfide bonds are covalent. And covalent are the intramolecular formula. So that's absolutely very important. So if disulfide is covalent, and we know denaturation is the breaking down of the intermolecular forces, like for example hydrogen bonding, so hence we cannot say that. Yeah, so that's wrong. Not all bonds are pretty much disrupted. So that's very important to understand. I hope that makes sense. D, the primary and secondary structure are disrupted when denaturation. Why did I write B is wrong? Okay, B is possibly a tick. We're supposed to write a tick. I don't know why I put it wrong. We just proved that it can disrupt that. What was that? D, the primary and secondary structure are disrupted when denaturation occurs. So the primary, remember, denaturation only disrupts the secondary, tertiary, and quaternary. So D is absolutely wrong. So B is your possible answer. Why did I put like a, yeah. So alcohol denatures protein by disrupting hydrogen bond. Yes, it can actually do that in some cases. So that's nice and easy. I hope that is a very good explanation. So question 16, a patient's blood tests indicate clinically low levels of vitamin C and D. Okay, what do we know about vitamin C? Vitamin C is polar, and it can be in your, as we can see, if we look at our formula sheet, have a look at this. These are, for example, let's have a look at this vitamin D in this case. There's two, but they look very similar. And can you see how this all non-polar, this very high, big non-polar group over here, and then you just get a little polar group here. So it's overall non-polar. Overall, we know that vitamin D, this one here, is non-polar. So that's very important. What about vitamin C? So vitamin C is, in this case, it's over here. And it's actually polar because it has all these OHs which can form, all these OHs. So it is polar. So that's the difference between them. So knowing that, great. Which of the following recommendations would most effectively and safely increase the patient's level of both vitamin C and D? Take a supplement of oil containing vitamin D. Good. Oh yeah, by the way, vitamin D, you can take it from the sun. Vitamin D, if you don't know, it's from the sun. So it's not what we call, it's not as important in terms of dietary. So whereas vitamin C, we have to consume it. We have to consume it for food. Did I just forget the word that we use for that one? Essential. Essential. So vitamin D is non-essential, whereas vitamin C is essential. You need to consume it in a diet. So take a supplement of oil containing vitamin D. Yeah, you can do that, but you can also take it from the sun regularly and eat a citrus fruit daily. So citrus fruit, again, is vitamin C. It gives you vitamin C. That's good. And vitamin D. That's a safe method. That works. We'll put a tick on that. Eat more dairy products. So dairy products have normally vitamin D. And spend 1 hour per day in the sun wearing sun protection. So also vitamin D. Both actually have vitamin D. We're not talking about vitamin C in this case. So here we're trying to get vitamin C also. So that's wrong. B is wrong because both of them are talking about vitamin D. C, dissolve a vitamin C tablet and vitamin D tablet in a glass of water each morning and drink it. That is true, but guess what? Vitamin D, it doesn't dissolve in water because it's non-polar. C is wrong. Eat more greeny leafy vegetables and spend 1 hour per day in the sun without wearing sun protection. Okay, now this is not safely. So, because not wearing, you will likely get cancer. It's not good for you. So, A would be your possible best answer for that one. Question 17. Shows below an infrared spectrum of an organic compound. As you can see, okay. The organic compound that produces this spectrum is what? Okay, now, a lot of students would go to the data book and see, what are the peaks and stuff. You should also know, guys, that this is very important. And this is a very helpful tip, especially dealing with these kind of questions. Start to memorize some specific patterns when look at infrared spectroscopy. For example, let me tell you. There are, for example, when we're looking here, if we have a strong peak meaning that its transmittance is very strong, so it looks like it's like this, or like pretty much like this, one. For example, this here is a strong peak because it goes its transmittance is very high. So here is a strong peak. If we have a very much a strong peak, that's why we actually kind of describe it. So having a strong peak, okay, let me just tell you. These are some common patterns that you'll see in an actual... So, for example, you will always see in this section around this part over here on the left-hand side, if you have a big molecule that looks like this, it has a strong, so first it has a strong, so it has a high transmittance, and it's very wide, for example, like this. This over here likely will be an OH group. And it will be an actual acid. So likely will be an acid if it's very, very big, like this in case. But, so what about if, also there's a case that there's another part that could be like this also. So also this is an OH group, but here is an actual alcohol. So in other words, what we can say here is, can you see how they both have a strong peak, but one is narrow, whereas one's kind of bigger, so narrow and one's very thick. So that's what we're saying. So just knowing that can actually quite help you. So yeah, that's very helpful. So for OH, just pretty much overall, OH, it needs to have a very strong, it's very strong. So it has a strong transmittance. That's important. We can, well, also at 1,700 centimeters -1, so over here, if there is a strong peak and it's very thin, it's always going to be, this is so common, it's always going to be a COO pretty much. It always is a COO. So for a fact, I know for a fact when I'm looking at this, so here is 1,700, I know straight away this is a strong transmittance over here. Okay, so you can see it's a very strong peak here. So I know for a fact that this is likely a COO. Always. Just remember, it's very common when you see a strong transmittance at 1,700. Well, having a look at this one here. Remember when we talked about OH having a strong peak? This is not as strong as we might want it to be. Remember, strong peak is like this. It's very high. So it would have been like this. But in this case, it's in the medium. If it's in the medium, another word, this is another kind of pattern you might want to see. If you have a medium, for example, if you have a medium, like this, if you have a medium, so a medium broad, so it's also thin, but just a medium transmittance, and it's on the left side, it's like 99% NH, and NH is going to be an NH. It's going to have that group, NH. So an NH. So when I'm always in exams, I always tell students, so remember, this is a fingerprint region. We don't actually care about this part at 1,400. We only look at the left hand. So greater than 1,400. So 1,400. So this peak is very important. Also this peak. And yeah, from patterns, I don't even have to look at my data book. I know that this one's NH. Likely will be an NH. This will be a COO. And see which answer I can cancel out. And then if I'm still struggling, if I'm still like, struggling one, I will look at my data book. For example, let's look at an aldehyde. Aldehyde, what does it look like? It has an R, C, H, and a double O. It looks like this. This is the actual structure of an aldehyde. So we do have a C double O. That's great. So we do have a C double O. That's actually good. So it could be an aldehyde in the case of this. Oh, sorry. It cannot be an aldehyde because we don't have an NH. What am I doing? We don't have an NH, and this is an aldehyde. So it does have that C double O, but it doesn't have that NH. So not an aldehyde. See? What about an alcohol? So an alcohol is OH. Absolutely not. Remember, OH would have a very strong peak, which in this case we said it was NH, so likely not. B, C, an amide. So an amide looks like, so C double O, and it's N, H, and H. Looks like this. So we do have an N, which in this case we do. We also have a C double O. Yes, so amide looks very good. And what about an ester group? An ester group. Well, an ester group looks like this. So it's a C double O like this. If it's an ester group, we have a C double O, which is correct. But we also have to have a CO, which we don't look like we have. So your possible answer should be C. And that's what I always tell students. For example, always a hint. You can make your life very easy, especially, but when you're dealing with, well, in this case, it's a multiple choice question. Remember, just memorize some of these patterns, and it'll be like a key that helps you smash these questions, in a second. But normally in extended response questions, you do want to look at on the data booklet because you need, so they'd like to make sure you tell them how you got your answer. So that's, make sure to, for extended response question, always do that. So let's move on. Question 18. Ammonia NH3 can be produced by the reaction of hydrogen H2 and nitrogen N2 when the reaction takes place in a sealed container of a fixed volume on an equilibrium system is established. Okay, the equation for this reaction is shown. If you don't know, this is the Haber process. It's to create ammonia pretty much. So we know it's an exothermic reaction. Great. If the pressure and volume remains constant, when the temperature is increased, the forward reaction will what? So wait, the forward reaction rate will what? So we're talking about reaction rate. Be careful. Reaction rate, we are talking about collision theory. If we increase the temperature, what do we know? We increase the kinetic energy. Increasing the kinetic energy increases the reaction rate. So for the forward and backwards, they both actually increased. So we need, okay, so the reaction rate should increase. So C and D are wrong. So yeah, so when the temperature is increased, the forward reaction rate is increased because it's the collisions, so by the collision theory. And then what? It says NH3 is what? So the concentration of NH3 will what? So we're going to talk about Le-Chandler's principle here. So what's happened is, okay, because it's an exothermic reaction, this is what I like to do. So to know using Le-Chandler's principle. So because it's exothermic, we know energy is going to be released in the product side. For example, yeah, when you heat up a fuel and, when you put in your hand, heat is actually being released. So it's going to be released on this side. We're going to call it energy. And because think of temperature as energy. So because temperature is increased, imagine this is increased. By the Chandler's principle, it's going to be like, wait. This is too much. We have too much energy. We need to compensate. We need to get rid of some of that to bring, back to equilibrium. So what it's going to do, it's going to go to the left. It's going to shift to the left. So if it shifts to the left, what's going to happen to this concentration? Because this is on the product concentration will decrease. So it'll likely be B in that one. So increase and then it will decrease. Nice and very easy. So what about question 19? A Year 12 chemistry assignment requires students to quantitatively. So quantitatively means numbers, so like calculations. Quality is, descriptions on comparings and stuff. So Year 12 chemistry assignment requires students to quantitatively and qualitatively compare fossil fuels and biofuels. Which of the following identification would be most appropriate to this comparison? So first one is use a bump calorimeter to determine the heat combustion for both fossil fuels and biofuels. Look, this is a quantitative analysis because we are determining the heat combustion. Heat combustion is a number. And it's not like we're comparing. So we're not actually we're not, saying anything. We're not, comparing. So A is only, So using a Bell to determine the heat combustion for both fossil fuels and biofuels. Yeah, we only determine the heat combustion, which is a number. So that's only quantitatively. B, interview car owners to determine what petrol price would make them consider using biofuels. Look, interviewing, it is a qualitatively, because you are describing, you are talking, you are, so that's, but we're not, that's not including quantity. So that's not wrong, right? C, produce biodiesel from vegetable oil and compare the viscosity of biodiesel produced with that of a range of fossil fuels. Okay, so we're saying produce biodiesel from vegetable oil and compare it of biodiesel. Okay, so this is comparison, but we're not doing any calculations. So it is qualitatively, but not quantitatively. So C is wrong. D, find the reliable information that about the environmental impacts of producing fossil fuels and biofuels. So this is, again, qualitatively comparison. And then what we do is that, and the amount of carbon dioxide produced per liter from the... Okay, this one's great. D is great because it's talking about a qualitative analysis here. They're talking about the comparisons and the environmental impacts of producing fossil fuels. That's qualitative analysis. And then they talk about the amount, so in terms of numbers of how much carbon dioxide is produced. So D is your likely answer for that one. 20. The reaction below represents the discharge of a standard lead-acid rechargeable car battery. So we have this. Okay, so this is the discharge equation. And during the recharge cycle, the pH will what? Okay, so what's going to happen in the recharge? So remember, discharge is like the reaction is going forward. The recharge is going to be backwards. So here are going, so the products, these products are going to be your reactants in this case. So if we're, recharging it, what's going to happen? These are going to be produced. So can you see this 4H plus? Remember, if the H plus ions increase, what do we know? It makes them more acidic. Acid is like more, so the higher the concentration of H plus ions, the pH decreases because it becomes more acidic. So we know through a recharge cycle, we know that we are increasing the product. So we're producing more 4H plus ions. So the pH starts to decrease. So A and B are wrong because it's saying increasing. And what it says, and chemical energy is converted to electrical. Okay, remember, discharge, what's happening? Discharge is where we're going from chemical to electrical. So the recharge is the opposite, electrical to chemical, which is D, that one. Question 21. So the mass of caffeine in a particular coffee drink was determined by high-performance liquid chromatography, HPLC. The calibration curve produced from running standard solutions of caffeine through a HPLC column is shown below. Okay. A 5 milliliter alicate of coffee drink was diluted to this with deionized water. So we actually have a dilution factor here. What's our dilution factor? So we're going from 5 milliliters to 50 milliliters. So it's a 1:10 ratio. So the dilution factor in this case is just 10. A sample of diluted coffee drink was run through the HPLC column under identical conditions to those used to obtain the calibration curve. The peak area obtained from this diluted sample was this. Nice. Question 21. So the HPLC column used has a non-polar stationary phase. Okay, so if our non-polar, so we just say this is a stationary phase. And this here is non-polar. So if our stationary phase is non-polar, our mobile phase has to be polar. Because for example, if our mobile phase is non-polar, it's going to get stuck. Remember, non-polar likes non-polar. So it'll get stuck into our stationary phase. So we want them to not be kind of stuck together. So it's very important that our mobile phase has to be polar. So the most suitable solvent for determining the concentration of caffeine in this sample is what? So it's pretty much telling us what is our mobile phase, pretty much. What chemical should we use for our mobile phase? Well, remember, we want it to be very polar. Let's look at the first one. So we have carbon tetrachloride. So if we draw carbon tetrachloride, this is symmetrical. Symmetrical means it is So symmetrical means it is non-polar. Remember, by symmetry, if a molecule is symmetrical, it is non-polar. So that's not good. That's not our That's not a good thing. We want polar. Methanol, okay. OH, so that's polar. And it has a, and it has a very small non-polar side, so that could be that. Octanol, okay, it has not a polar side, but it has a much larger non-polar side. So in comparison to methanol, C would be wrong. Methanol is better. Hexane, okay, hexane, absolutely, it is non-polar. So B would be a possible answer for that one. The mass of caffeine in grams in 350 milliliters of undiluted, be careful, undiluted. So we're going to use our dilution factor to calculate this. So that's easy. So what I'm going to do first is go to my 2,400 RBD units and see where that is. It's right over here, actually. So where is our concentration? Our concentration is, let's write that down, 0.040 grams per liter. But remember, because we have a dilution factor, we're going to multiply this whole thing by the dilution factor. Because this is the diluted concentration. We want the undiluted coffee. So 0.040 times by that 10. Hence, we get 0.4. So we just want to get the mass, so the grams. And we just need to convert this to liters and then multiply by 0.4 and we get the grams. So what's 0.4 times 350 times 10 to the negative 3? 0.41. So C is your answer for that one. Nice. Question 23. The heat of combustion of a sample of crude oil is to be determined using a bomb calorimeter. All the students in the class are given the same method to follow. The apparatus used by the students is shown below. Okay. For these experiments, the students could maximize. So the first one is precision by using a digital thermometer of this. Okay, remember, precision is how precise are those values? So how close are those values? What is the range of those values? How close is it? So if you want to maximize, so make the precision very high, they're using a digital thermometer. Okay, so precision comes from random error. This is what precision is. So precision comes from random error. If we want to maximize precision, we need to decrease that random error. So what they've done is they're using a digital thermometer. Yes, a digital thermometer is better because it's more better. Like, in comparison to using a actual physical thermometer where we have to start to estimate, which creates, again, random error. It gives a high random error. A digital thermometer, a digital one is better because it decreases that random error, meaning that we are, maximizing precision. So A is actually correct. A could be correct. Let's check the other ones. Validity. So what is validity? So validity is how valid is the experiment? Is the experiment following the aim and the hypothesis? So validity by calculating the heat combustion per mole. No, be careful. I think this is going to confuse a lot of students because we are looking at crude oil. Remember, crude oil is a mix of all. It's a mix of all fuels. It is kerosene, petrol, diesel. It's a mix of everything. Using per mole, you remember when we calculate the heat combustion per mole, we need to know the mole, like the molar mass actually, also the molar mass. And remember the molar mass is, we know the structure. Like, if we were finding the molar mass of, let's say, methane, we know like how many carbons and hydrogens there are. But when we're doing crude oil, it's not a valid, because a crude oil is a mix of everything. We can't use that one. We can use per mole, but if we maybe use per gram, if it was per gram, yes, that's actually a great way. It's then valid because crude oil, we don't actually know. It's a mix of all substances. Using per mole is not a great way. So yeah, it's much more valid. It's not valid, pretty much. What we're saying, it's not valid. We are decreasing validity, so that was wrong. Be careful, yeah? Per mole, we need to think it's crude oil. C, accuracy by taking samples from 3 different sources. Remember, okay, accuracy is how accurate is the data. So how accurate are the values to the true value? That's what accuracy is. And accuracy is, could be, so remember, accuracy is all about the random error and systematic error. It needs to be including both. Systematic error. So if we want to have a very high accuracy to maximize it, we need to decrease both of them. both random error and systematic error. So if we are taking samples from 3 different sources, if you're taking from 3 different sources, remember different sources have different amount of, fuels. For example, one could have high petrol, one could have, diesel, and remember, it is crude oil. If you're taking 3 different sources, if maybe the question said taking from the same source, then it makes sense. But if you're taking 3 different sources, so the crude oils all are different, what you're doing is you're increasing the likelihood of random error. Because so remember, if we wanted to maximize it, we wanted to decrease random error. But here, using 3 different sources from other places, we are actually decreasing. We are minimizing the accuracy. What about D? Uncertainty by having all students closely follow the same experimental procedure. So that's wrong because, the good thing is, if we want to, normally we want to minimize uncertainty. I don't know why we want to maximize it in this question. So normally when we want to decrease uncertainty, what we do is, yes, we closely follow the experimental and we bring having more students. So having all the students closely follow the experimental procedure, that's great because what it does is it decreases systematic error, which is great. So if it decreases systematic error, the value of the uncertainty goes. But we want to maximize it, so that D is wrong. So again, if having all students do the same, experimental procedure, we pretty much decrease systematic error, hence uncertainty decreases, but we want to increase it, so D is wrong. So only possible answer is A. Okay, question 24. It says, a sample of olive oil with a wick in a jar is ignited and used to heat a beaker containing 500 grams of water, H2O. The relevant data for the experiment is included in the table, and we have the initial temperature, the change in H, total energy lost to the environment. So after the complete combustion of 2.97 grams of olive oil, the final temperature of water in degrees Celsius is what? Very nice and typical question. So what we're going to do is we're going to get this change in H. So 41.0 is equal to kilojoules per gram. So kilojoules per gram. So because we're talking about olive oil, so how much mass do we have of olive oil? And we can actually calculate the energy because we can sub that in right over here and calculate kilojoules by multiplying them together. So what is 41 times 2.97? It's 121.77. We want to change it to joules, so times it by 1,000. We get actually 121,770 joules of energy. So joules of energy. That's our energy. Now, what we're saying is this is considering all the energy has actually gone to the water. But remember, we have some energy that is lost. I should have actually, this is, so this is our total energy minus the 28 times 10 to the power of 3. This is the energy loss, and because I should have just left it in kilojoules, but also just convert it to joules, makes your life easier. So convert that to joules and minus it from the total energy, so minus 28 to the power of 3. So hence our energy we have is 93770 joules that have went to the water. Now we're just going to use MC delta T to calculate the final temperature. So we know that's going to be the energy is going to equal to mass. So what's the mass of the water? We have 500 grams of water times 4.18, the specific heat capacity of water, times your change in temperature. So hence your change in temperature is what? Let's do the calculation. So it's that 500 times 4.18, and that gives us 44.86. So we have that, and that is the change in temperature. Remember, the change in temperature is TF, so it's final minus your initial equals 4.486, and we know the initial temperature is this, so your final is just at 44.8 plus the 21 degrees, which gives me the total of 65.86 degrees Celsius, giving us the answer C. Nice. Question 25. The glycemic index indicates how quickly carbohydrates in foods are broken down and rates a person's blood glucose level. The table below shows the percentage of amylose and amylopectin, I still say that word, I don't know if I'm saying it right, in the carbohydrate content of 4 foods. So we have 4 foods. Based on this information, which of the following foods listed would be expected to have the lowest GI? Remember? So what they told us is the highest GI is how fast, it depends on, so having a high GI means the food is broken quicker. So, okay, so having a higher GI, we know if we go to our data book and let's look at we have amylose. So let's look at amylose. Where's amylose? Amylose is here. Looks like amylose. Amylose and amylopectin, which is here. What can we see between them? Well, we can see that amylopectin has a lower melting point because why? Like it can be broken down easier because it has branching. Can you see these branching, these open parts over here? So when heat is produced, it's going to break those branching quicker and easier. So we know that amylopectin, so it's going to be broken down faster, meaning that the GI, so your glycemic index, is going to be higher because it's easily broken down. So meaning that we want, for a high GI, we want high amylopectin, pretty much. Okay, and so what about the amylose? Well, amylose is actually it has a much higher it's much harder to break because it is it's kind of straight, it's a linear in comparison to amylopectin. In comparison to it, amylose is much stronger. So if we want food, so we also want lower. So we want a lower than amylopectin. So we want a low amylose content. So overall, we want foods with high for high GI. We know amylopectin is going to be very high for high GI, and we want amylose to be low to have that. But we want the lowest GI food. So for the lowest, it's going to just be opposite. So the lowest, the signs are just going to be the other way, pretty much. So we want the lowest amylopectin percentage. Which one has that? So amylose, we want the highest. So this one here has the highest. And the lowest amylopectin, which is this one over here, comparison to what? So A is your answer. So food P would have the lowest GI. Hope that makes sense. Question 26. 10 grams of carbon dioxide, CO2 gas, is injected into a sealed, evacuated 12-liter vessel at 30 degrees Celsius. So what's happened is we have a vessel, for example, this vessel over here. And initially, let's talk about it. So what do we, it's not. So this is the vessel, and we know that it has 10 grams. So 10 grams of CO2. It's a 12-liter vessel, and it's at 30 degrees Celsius. Great. After a further 1 gram of CO2 gas is injected into the vessel, what is the temperature change in degrees Celsius required to maintain the original pressure? Of course, we're going to have some pressure. Let's say this is the original pressure. And what's happened is they've just added an extra gram into the so inside the vessel. What's going to happen then? Well, of course, what's going to happen is that it's going to be now 11 grams inside. It's still 12 liters. And what is that change in temperature? What's the temperature? And then we just find the difference between them. That's going to give us that change in temperature. And we said that what is the temperature change in degrees Celsius required to maintain the original pressure? So this is our original. So we want the same pressure. Okay. So let's calculate the pressure using this over here. We know we're going to have to use PVNRT, which can be found in your data book, if you don't know. So PVNRT. And we want to calculate the pressure, which is just nRT over V. So what's that? So pressure, what's your number of moles? Well, because we have 10 grams of CO2, so CO2, so C is 12 plus, we have 2 oxygen, so 16 times 2. That gives us the mole of 0. So it's going to be, Well, let me actually move these all. There isn't a lot of space, so bring it here. So pressure is going to be, so the number of moles is going to be 0.227 times your R, which is 8.31. It's the constant temperature. It's going to be needed in Kelvin. So 30 degrees, so 30, what's 30 plus 273. And that's all going to be divided by the volume. Let me put this here. The volume of the vessel, which is 12. What's our pressure? Let's calculate that now. 8.31 times 30 plus 273 divided by 12. And the pressure is 40. So your pressure that this is going to have is 47.68. And remember, for both of them, we want the same pressure. So kilopascals. So we want both of them to have the same. This over here, we want 47.68. Now, yeah, let's calculate the change in temperature now. Let me just rub this off. And again, using PV and RT, so PV, and we want to calculate the temperature. So it'll be, temperature is going to be PV NR, which is what? So temperature is pressure, which is 47.68, times your volume, which is still 12 liter, and that's divided by the N value. So the moles, and remember here we have how many moles of, we have, so what's 11, the mass divided by the molar mass, which again is 12 plus 16 times 2, and that gives us 0.25, times your R value, which is 8.31, that constant. So let's write all those down. So 47.68 times 12, 0.25 times 8.31. And that gives me 275 point something. That's in Kelvin. So we're going to minus 273 to get it into degrees Celsius. That's going to be, our temperature is 2.4079 degrees Celsius. So what it's saying is, if we want to maintain the same pressure, the 47, what's happened? Well, we were originally at 30 degrees Celsius, and we need to decrease the temperature to 2.4 for us to have the same pressure. So what's that change? So what's just 30 minus that? It is 27.59, which is just 28. So these are wrong. But it's going to be minus, because remember, we're going from 30 to this. We need to decrease that temperature. So A is your answer. Hope that makes sense. Great. Questions 27 and 28. An increasing popular battery for storing energy for a solar panel is vanadium redox battery. The battery takes advantage of 4 oxidation states. 4 oxidation, okay, of vanadium that are stable in aqueous acidic solutions in the absence of oxygen. The schematic diagram of vanadium redox battery is shown. Okay, what do we see? We can see that there's 2 for each, so 2 in each pretty much storage, and so one side's going to be oxidizing and one's going to be reducing. So, but we're going to have 2. So these 2 here are probably going to both be oxidizing. Probably these ones going to be reducing, or vice versa. So one of them, yeah. So we're going to have 2 stuff that are going to be from this question. The 2, okay, so they give us, so the 2 relevant half equations for this battery is shown. The overall reaction that occurs when the battery is discharging is what? Nice and easy. Well, if we know there's E values, remember, the highest E value, so for example, this one over here has, like, it's going to be reduced. So this one over here is going to go through reduction. And here is going to go through oxidation. So what we do is just, we kind of like swap this around. So it's going to be like V2 plus AQS goes to E minus plus V3 plus AQS. So let's write that up. And then add them together. So those electrons will, so those electrons will cancel out. So it'll be this, plus this, which is what? So VO2 plus, which one has that? plus 2H plus, so it has that, plus V2, yes. And then we have to have this, plus this, plus this. So VO2, that's great. H2O, which is here, and V plus, yes. So A looks like the best one for that one. Yeah, that's an easy, that's not too bad. Let me just rub this whole thing now. Too much mess. So, okay. Alright, question 28. If air is present, the following half equations are relevant. Okay. If air is present, so we have this and those. Okay. Again, if air is present, which one? So VO2 aqueous ion is oxidized. Okay, let's find which one's oxidized. Remember, so same thing. Which one has the I's E value? So this E value, which in this case has, it's this one. So this here is going to go through reduction. And which one has the lowest E value? It's actually this one. So this one's going to go through oxidation. So in other words, where this one, so because we're talking about oxidation, well, the first one saying VO2 ion is oxidized to V2 plus. No, so which one goes for oxidation? This one. So V2 plus aqueous goes to V3 plus aqueous. That's the one that goes for oxidation. Let's see which one looks like that. So V2 plus aqueous. So yep, so V2 plus ion is oxidized to VO2 plus. What's that VO2 plus? No, it's V3 plus. So C is wrong too. The other one's saying this one is oxidized. That's wrong too. VO2. It's V2 plus that's being oxidized. VO2 is reduced. No. Oh, well, let's actually, wait, VO2 is reduced. This one's going to be reduced, so it's not anything like that. And this one's also wrong. What? Am I wrong? No. Wait. Let's think again. Let's look back to the question. Takes advantage of 4 oxidation states. Oh, no. Okay, guys, wait. This is where they've given you the hint. Okay, when we said, so we know the one that was going for oxidation is this one, yeah? This one over here. So we said that's going to become V2 plus and it's going to go to V3 plus ions. And what does that mean? Okay, so which one's has the V2 plus here? It's this one over here. So this part over here is going to be oxidation. And this part is going to be the reduction side. So if V2 plus, what it's saying is, because, you know, V2 plus, it's all being transformed. So it's oxidizing to V3 plus. So what's happening is this over here is making, so this V2 plus is making V3 plus ions. But because we're both on the oxidation part here, this oxidation part here, so it means that also when this is making all that V3 plus ions, this is going to also go through oxidation. And where is that? So now it's going to go to this one over here. Because that's it's going to go into this one. Which here, V3 plus, and it's going to go this way. And that's going to, so this V3 plus is going to create VO2 plus. So, yeah. In other words, when we started with V2 plus, so this V2 plus here, V2 plus aqueous, we pretty much went and created, it actually oxidized to VO2 plus. VO2 plus. So, VO2 plus, no, so VO2 plus. I hope you a little bit understand that. So, again, so let me just explain it, because it's actually such a, I don't like it, because it's actually quite strong, it's a very, very hard question to understand. So let me explain it again. Let me slowly explain it. So we know basically that this part over here is oxidizing, and this one here is reducing, this part over here. Now, what do I know? That imagine that all of this, so we know it's going to go this way, because you remember, imagine flipping this around, because it's oxidizing. The electrons has to be on the right. So we're going, so V2 plus, we can say that. So V2 plus aqueous is actually oxidizing to V3 plus aqueous. That's true, yeah? So what we're saying is when we have V2 plus, it's oxidizing to V3 plus. So it's creating V3 plus. But if you look at this, they are in the same oxidation vessel. So if we're if we're starting with V2 plus and we're creating V3 plus, this V3 plus is also going to go through oxidation. So yeah, so when V2 plus runs out, so imagine like currently we have a lot of V2 plus. Currently we have V2 plus, a lot of it. And as time goes and progresses, we are creating V3 plus, and after some time we finish the, we don't have any more V2 plus. And now we have 0 of this, and now we just have a lot of this. But guess what? Because we know both of them are going to go, this whole thing, the whole vessel goes through oxidation. Now V3 plus is going to go through oxidation. So what is the next, remember this was the lowest, now what's the next lowest? It's this one over here. And that's the V3 plus, and now it's going to go through oxidation. It's going to go to the left again. So V3 plus is creating now VO2 plus. So VO2 plus is, so yeah. In other words, the V3 plus, we call this a stable intermediate because it just cancels out pretty much. Let me kind of write the equation and how I'll, I know it's a lot. I know this one's actually quite confusing. A lot of students will get confused because it's, yeah. So you know how, okay, this is our first step. A lot of students get this first step right. Imagine now we also know this step. And let's write that down. So VO2 plus AQS plus 2H plus AQS plus electron goes to V3 plus AQS plus H2O. Have a look at this. Can you see how the now they're both on the opposite side, so we can actually cancel those electrons out? And also the V3 plus are oh no, actually that's not a good expression to even do. I feel like that will confuse students a lot. Not a good way. Yeah, so I hope that a little bit makes sense for this question. Again, so when we run out of V2 plus, when all of it's used up, we now have so much of this, but remember it's still also going to go through oxidation. So we started from this and we finally, it gets reduced to this V2 plus AQS, meaning that, so we started with V2 plus AQS and we oxidized to VO2 plus AQS, which is C as that one. Hope that makes sense. Took too long on that question to explain, yeah. 29. The following energy profile diagram shows the results obtained during an enzyme catalyzed reaction. Each stage of the reaction is labeled M, the initial reactant, N represents a stable intermediate, and P represents the final product. Which of the following statement correct is correct? Okay, so if you don't know what a stable intermediate is, like we pretty much, this is what it is. So the first step is when we're going from M to N. So M plus N, M goes to N, yeah? And what do we know? Like if we're going from M to N, remember, just ignore this right now. What do we know? Well, it's an endothermic reaction because as you can see, the change in H, so from here to here is endothermic, so it's a plus, we'll call it plus 20 in this case. So it's endothermic. And then we're going from N to P. So the first step is going from M to N, so all that reactants is used up and it's created this product, and now this product is going to be used up to create P, the final product. So now it's like we're going from N to P. And now, because this here is like a exothermic and it's much less than, so we say like -15. We're just making values. What do we see? Remember when we add two equations, you know that N, how it's a stable intermediate, it cancels out. So when you add those two up, they're going to cancel out. And then we're just going, M goes to P. That's your final. So your reactant goes to products, which is that. And, you know, by Hess's law, these here add. So 20 minus 15, that's a plus 5. So the overall from M to P is an actual endothermic reaction, which is true because you can just go from N here. So if you just go from M here to P and look at it, it is a greater than, the change in H is greater than 0. So yeah. Let's look at the questions. The energy changes from M to N M. So from M to N is exothermic. No, it's endothermic, and we even gave it here. From M to N is plus 20. So that's wrong. The energy changes from M to P. So M to P, which we here, is exothermic. No, M to P is plus, so it's endo. And also we've also shown it here. The energy changes from M to N is endothermic. That's good, yeah. And the energy changes from N to P is endothermic. No, N to P is exo because it's negative. So C and must be D. The energy changes from M to N is endothermic. Great. And the energy changes from M to P is also endothermic. And we've said that. Nice. The final question. That is so tiring. I'm already tired. The diagram below shows the basic setup of a electroplating cell. Initially, the cell is set up with a lead PB electrode as electrode Z and a 1 mole lead nitrate as the electroplating solution. The cell runs for a set time and current with 1.0 grams of PB deposited on the electrode Z. Okay, so we have 1 gram of lead deposited on electrode Z. Four subsequent electroplating cells are set up, each containing a platinum PT electrode at different electrode Z and an appropriate 1 mole electroplating solution. These 4 electroplating cells are operated at the same time and at the same current at the original lead electroplating cell. Which combination of electrode Z and electroplating solution would be expected to deposit more metal by mass onto electrode Z than the original PB electroplating cell? Okay, so what we want to have a greater which of these over here will give us a greater than 1 gram of mass deposited into that electrode Z. Okay, how would we do this? Let's think. Okay, because they tell us that the operated for the same time and time, the current is the same and the time is the same for all. Okay, have a look at this. If we know that from the formula that what do we know? So 1 gram, so what's PB? Okay, well, in this case, we have a PB2 plus from this. So if I was writing the reaction for PB, so it'll be PB plus 2S plus 2E minus goes to PB, solid. Now, what we have here is we have 1 gram. So we have 1 gram of the PB lead. So let's convert it to moles, and we want to solve for electrons. Okay, so let's do that. So 1 mole. So for a mole of PB, which is going to be mass, which in this case is the 1 gram divided by the molar mass of PB. What is that? Let's check that. So where is PB? Oh my god, I have to count. PB is 207.2. Let's write that down. So 207.2. Yep. If I again. Yep. Okay. So it's that. Okay. And that's gonna give me, so what's 1 divided by 207.2, and that gives me 0.00482 mole. And now by ratio, so if we want the mole of the electrons, it's just going to be this over here multiplied, so it's the N of PB multiplied by if we go into this, so we want 2 over 1, so it's just going to multiply by 2. Imagine multiplying by 2, we get overall 0.00965 mole. Now that's very easy. Now that's very good, because now we have this. We know that in our formula sheet we have the mole of electrons is equal to the charge over Faraday's law, and Faraday's law is a constant, which is 96,500. So what's this over here times that to get the charge? 965, so 9 times 96,500. So we get the charge to be 931.46. And remember, charge is equal to the current times time. But wait, the current times time are the same for all the reactions. So the charge is the same. So we can use the same charge for all of them. And remember, so charge divided by Faraday's law. Remember, Faraday's law is just a constant. That's actually, yeah. So what's that charge again divided by that Faraday's law? We'll go back to the original. Yeah, so for all of them, pretty much what we're saying is, so in other words, for all of them, the mole of electrons is going to be same for all the, the new questions, the ones, yeah. Let's do the first one. So it says chromium. So if we're using chromium, so here it says chromium. So what's chromium? So it's going to be Cr3+. So if we have chromiums, we need to add 3 electrons, and that's going to give us C3 solid. So we have the number of electrons, and we want to calculate the mole of Cr, which is going to be, so the number of mole of electrons is going to be 1/3 times 1/3. So what's times that? 1/3. And that gives me 0.003217 mole. And remember, we want the mass. So the mass of chromium that will be deposited is the mass over the molar mass of chromium. It'll be that times the molar mass of chromium. What is chromium? If we look over here, oh my gosh, I have to twist my neck. Chromium is 52. So imagine multiplying by 52, we get 0.167 grams. So okay. So that's for our first calculations. That's it. So we get, let's wrap that all out. So for chromium, this gives us 0.167 grams. We have to do the same for all of them, pretty much. Just the same calculations. Now it's easy. Like, we got the first one. So the next one is, so writing this, so we know it's written as Ag plus E minus goes to Ag solid. And remember, we're still using the number of electrons the same. So it's a 1-to-1 ratio. So the number of electrons is the same number. So the mole of Ag is the same as the number of mole of electron, which is 0.00965. So what's the mass of Ag, which is just the number of mole times the molar mass. So let's do that, 0.00965 times. And what's the molar mass of Ag? So silver. Let's look at it over here. And that is, where is that? Ag, oh my god, it's so much. Okay, we have Au. Or Ag, where are you? Ag, 107.9. So 107.9. That gives me 1.1. Yeah, is that 107? So Ag is, yeah. So that gives me 1.04 grams. That's good. So let's write that down. That's going to give us 1.04 grams. So okay, it's much than that. Same thing. Let's do the same for the other one. So Au is going to be 3 plus 3 electrons goes to Au solid. So what do we know? It's pretty much going to have the number of moles of Au is going to be number of negative electrons times 1/3, which is the same as this one over here, but which is, what's the number of electrons? So 0.00965 times 1/3. And now we got the number of moles. And that number of moles we're going to multiply by what is Au. What's the molar mass of Au? I'm doing this in my calculator. I hope you guys understand. I know it's a lot. It's a very tedious calculation, but I just want to show you how to do the question. Normally you can go quicker. So 197. So 197. And that gives me a mass, we can say, of this whole thing. 0.6 grams pretty much. The next one is this, which is SN2 plus 2E minus goes to SN. Okay, so it's going to be the number of moles of SN is going to be number of moles of electrons times 1/2. So again, let's do that. So 0.00965 times 0.5. Wait, sorry, what happened? 0.00965 times 0.5, and we got that, and then we just have to divide it by the molar mass. Sorry, times it by the molar mass of SN. So where is SN? What is SN actually? So 10. So SN 10 is 118.7. 118.7, and that gives me overall 0.57 grams. 0.57 grams. Overall, the one that creates the most more metal is this one over here. So silver. I hope that is easy to do. It's very long and tedious, I'm not gonna lie. So I hope you guys understood how to at least do that question. And yeah, that's the final question. I hope you guys learned something from this video. Please make sure to like and subscribe so I can make more future videos. You know, it gives me kind of the motivation. And thank you guys for watching. Please take care of yourselves. Bye bye.